Thank you for the introduction. Again, my name is Nathan Clayburn. I'm a postdoc at Amherst College working with Larry Hunter. I'm excited today to have this opportunity to share with you our work involving optical cycling of thallium fluoride. I want to start by putting our work in context. I want to talk about our goals and our motivations. And to do that, I need to talk about a topic which was already mentioned in this session, the baryon asymmetry. So I'll go through this quickly. So when we look out into the universe, we see this imbalance between matter and antimatter. And this is a problem because all known physical laws should treat them equally. Neither the standard model nor general relativity provide an explanation for this asymmetry, and what's required is CP violation beyond the standard model. And this new CP violating physics creates observables, the classic example of which is the electric dipole moment. The existence of these EDMs requires parity and time violation. Our good friends at the Centrex collaboration are searching for one such EDM of the proton. So a proton EDM will lead to deformation in the shape of the atomic nuclei, known as a shift moment. Centrex will search for the shift moment and the thallium nucleus inside a thallium fluoride molecule. The observable signature will be a shift in the NMR frequency of the nuclei when the molecule is polarized in a strong electric field. The details of that experiment can be found here. Additionally, there are some members of that collaboration in the audience who I'm sure would be happy to discuss their experiment in detail. But essentially, after some state preparation and some precession, ultimately the final internal state of the molecule must be read out. And that's where we come into the picture. So we are specifically interested in optical detection of the molecules in that detection region for the first generation. And looking forward to the next, we're interested in potential transverse cooling of the molecular beam. So we have sort of two questions which we hope to answer. The first is, can thallium fluoride be made to cycle many photons? So to achieve the desirable sensitivity, the molecules must be detected with unit detection efficiency. So detection depends on, of course, many factors like efficiency of collection optics, but essentially, if your molecule flies by and emits one photon, you're unlikely to see it. However, if you can get it to cycle many photons, 10 to 100, that should allow for internal state detection of the molecule. The other question we're interested in answering is, can we transversely cool thallium fluoride? So, of course, when a photon is absorbed by a molecule, the velocity decreases by momentum conservation. Each of our photons has about recoil velocity of about 6.6 millimeters per second. So to achieve transverse cooling for us takes about 250 photons. So with that in place, let's talk a little bit more about our molecule. So in 2012, some studies by our group were done. At that time, favorable Frank-Condon factors were measured. They were in general agreement with theoretical predictions. Also at that time, the lifetime of the state, the relevant state, was measured to be 100 nanoseconds. A little bit later in 2017, a follow-up study was done to investigate the hyperfine structure. Observations were made with both a thermal beam and a cryogenic beam, and that allowed access to a large range of rotational states for classification. So here we see the thermal beam in green and the cryogenic beam in black. That work was done by a number of individuals, including some of our speakers. Danny spoke on Thursday, and Eric will be speaking a little bit later on today. But what I want to do now is kind of summarize the important features, what these studies are telling us. These will come up throughout the remainder of the talk. So the first thing I want to draw your attention to is this absolutely massive hyperfine splitting in the excited state. And this is not a typo. It really is 13 gigahertz. And what that means is that our laser is only going to excite to a single hyperfine state in that excited state. This is attributed to an unusually large value of this H1, which we believe may be the largest observed hyperfine interaction in the diatomic molecule. Another interesting feature of thallium fluoride is this ground state has very small splittings. It's degenerate, and we'll talk about what effect that will have a little bit later. I also want to mention that our excited state has strong J mixings. So we're going to have rotational closure for only a few select states. Finally, I'll just mention that in the presence of fields, one would have a small Zeeman shift in the X state. However, one would have a large Zeeman shift in the excited state, and that's going to be an obstacle for magnetic remixing. So with those details in place, let's talk a little bit about optical cycling. So of course, molecules are more complicated than atoms because molecules can decay to rotational, vibrational, and other kinds of dark states. For us, we have 4 dark states that we worry about: vibrational, rotational, polarization, and hyperfine. I'll go ahead and talk about those each individually in detail. So I already hinted at this, but those earlier studies identified a quasi-closed cyclane transition. So with a single laser at 271 nanometers, one could expect to cycle about 100 photons. With 2 lasers, one could expect to cycle about 1,000 photons. So that's going to put an upper limit on the number of photons we can expect. We also worry about rotational dark states, but of course selection rules limit the accessible rotational ground states after excitation. So if we consider a Q transition, delta J equals 0, and think about its possible decays, we see that it can only actually decay back where it came from, and that's because the rotational parity of the ground state goes as -1 to the J. It's a little bit more complicated than that, of course, because one can have excited state hyperfine interactions that mix rotational states with different quantum numbers, and that can break the usual selection rules. So in this example, we have this admixture, for instance, would allow decay to this J equals 3- ground state. So specifically for thallium fluoride, we've identified 2 transitions with little admixing which remain closed, shown in red and green here. And I'll just mention that other transitions in that same hyperfine manifold remain open, like this blue transition here. So we also worry about polarization dark states. So laser light, of course, couples via the electric dipole operator, and total angular momentum must be conserved. So we have transition rules. And if we consider a Q1 transition with hyperfine structure ignored, and imagine we excite it with sigma plus light, what we see is we have this polarization dark state in the m equals +1 level. We can overcome this, however, by quickly modulating our polarization. So in this example, we alternate between sigma plus and sigma minus, and what was once a dark state becomes bright and vice versa. This is essentially modulating this polarization can help us eliminate these polarization dark states. Perhaps most importantly of all are hyperfine dark states. Now, these arise due to the unresolved hyperfine structure in the ground state. And what happens is that when one excites to a single fully resolved upper state hyperfine level, the exciting laser couples at most a single superposition of that ground state. All the other linear combinations are going to remain dark. I've attempted to show that here, so this shading represents addressing a single linear combination. So these hyperfine dark states evolve in time, but you must wait for these dark states to evolve into bright states. You can play tricks, which we will discuss, to help to stabilize them using polarization modulation and other excitation schemes. So talk a little bit more about these hyperfine dark states. I want to show you a simple toy model. So both Olivier and Conrad have done a lot of thinking about this. But what I want to show you is a toy model that sort of maps onto the structure we're talking about. So imagine I have 2 ground states separated by some small splitting, and I excite that with some Rabi rate and some detuning. So to describe that, I write the Hamiltonian, and then to better understand it, I write it in a basis where I can see how the bright and dark states are connected. I see that the bright states have direct coupling to the excited state. I see that these dark states have indirect coupling with the bright states with a coupling strength proportional to that very small splitting. The takeaway here is that these dark states evolve with a rate which is proportional to that small ground state splitting. So, tying that all together, we've identified 2 transitions which are highly closed to these unwanted electronic, vibrational, and rotational decay paths. So the Q1 F prime equals 0 and the Q1 F prime equals 1. Uh, Before I move on, though, I do want to mention some sort of, I guess, unique feature about thallium fluoride is that we're working with a singlet to triplet transition. And this is different from other cold molecules being investigated, as shown in this nice review article. So many of our complications are related to this structure, that resolved excited state and that unresolved ground state. So I just want to talk briefly about our apparatus. We have a typical cryogenic buffer gas beam source. We guide our beam through some collimating apertures to our interaction region. In that interaction region, the molecular beam passes through resonantly tuned UV laser multipass, and then we capture the molecular fluorescence with a detector. So here's our molecular beam in green, here's our multipass in blue, and here's our detector in red. So this multipass does a couple things for us. It increases our interaction time, and it also helps to make our beam intensity more homogeneous. So we can take a couple different kinds of data. We can simply record the fluorescence as a function of laser frequency. This technique has no spatial resolution, but good signal to noise. The other thing we can do is we take camera images. So the units here are pixel values. So in real space, this is sort of 2 inches by a little more than a 1/4 inch. Our molecular beam's coming in from the left, and then we can make graphs by taking sort of summing over vertical strips for each value of x. And we can get graphs like this, and this tells us a lot about what's going on. There's a lot of information contained in these pictures. So that's the kind of data we can take. Let's talk about optical cycling. So how do we figure out how many photons we're cycling? Well, what we do is we compare the peak heights of these transitions of interest to our calibration transitions, and because fluorescence is proportional to cycling of the transition, those quantities are related by this expression. So put simply, if this is my, say, calibration transition, I somehow know that it cycles 9 photons, and I measure my transition of interest, and it's 4 times higher, then I know I'm cycling 36 photons. Now, of course, one also needs to account for state degeneracies and differences in ground state thermal populations, but those are all things that one can do. We can also take these standard candle measurements with our camera. So here I have 2 transitions, one which cycles in red and one which does not in blue. And we see that the one that cycles in red, we see that the fluorescence remains relatively stable throughout the interaction region, meaning the molecules are still cycling as they traverse that final multipass. Our calibration transition in this instance is limited by rotational branching and sort of lacks fluorescence midway through that path. So we performed a bunch of measurements, and what we found was a cycle time that was significantly slower than a simple model would predict. And this in and of itself is not particularly surprising, but what became very obvious is that these simple models failed to describe the effect of these hyperfine dark states. So these hyperfine dark states dramatically reduce the photon cycling rate of both our transitions of interest and our calibration transitions. And what we needed to do was develop more complete simulations, things that solve the optical Bloch equations, track trajectories, account for laser intensity profiles. And so we did, and that work was done by Oliver, Jakob, and Ascari. Oliver led that effort. And you can ask the question, what do these simulations tell us? So the first thing is that these simulations indicated what the best standard candle was, what the best calibration transition was. So what does one want in a standard candle? One wants a standard candle whose fluorescence is limited by some easily predicted mechanism, something like polarization dark states or rotational branching. You want that standard candle to be insensitive to parameters like beam intensity. But in either case, these hyperfine dark states are also going to contribute to reduced cycling. And what the simulations indicated were that these R1 transitions are robust standard candles. So here's an example of the output of those simulations. So here's the ground state population for j equals 1 and for j equals 3 as a function of time. And I've sort of color-coded them, and I'll try to keep that color code throughout the talk. So we see these bright states whose population rapidly decreases. And then due to rotational branching, that population accumulates in this j equals 3 minus level where it ceases to cycle, sort of in the gray color. We can also see hyperfine dark states in red, and we have just a spectator state here in green. So we have these simulations, and we can do the experiment. So here's what we do. We're going to try to confirm the accuracy of the simulations by comparing each value of these R1 transitions and using them as standard candles to estimate the number of cycles for the other R1 transitions. There's a lot of information here, so we'll go through it slowly. So each row is a different standard candle, a different calibration transition. These columns are our test transitions, our transitions of interest. These bottom two rows are the number of photons predicted by our simulations, and here's the number of photons predicted from a simple branching calculation. So I want you to focus in on one of these columns. So here we're measuring the f1 prime equals 3/2, f prime equals 2 transition. And what I want you to see is that no matter which standard candle we use, we get about 2.5 photons. And what's more is that is in pretty good agreement with our simulations and less so with that simple branching calculation. And if we sort of zoom out and look at all these columns, we sort of see sort of everything's sort of internally consistent and in good agreement with our simulations. So that's giving us sort of confidence that our simulations are describing our experiment. We can also use these simulations to help us guide our selection of cycling schemes. So the simulations confirmed this idea that we actually need a third orthogonal polarization to obtain cycling near the vibrational limit. And here's how we do that. So here's my molecular beam in green, and here's my original multipass in blue. And what I've done is added another multipass in purple. And what you need to do is modulate the polarization of both that horizontal multipass and the vertical multipass like I've shown here. So modulating just the horizontal will result in modulating two orthogonal polarizations, sort of in this coordinate system, x and z. And the inclusion of that modulating vertical multipass allows a polarization projection in x, y, and z. So I'll just denote the first situation as xz and the second as xyz. So what effect does this additional orthogonal polarization have? Well, for the f prime equals 0 case, it's going to remove that additional dark Zeeman state from the cycling transition. That should increase cycling. What about for the f prime equals 1? All the dark Zeeman states are already destabilized, but this third polarization is going to excite a different linear superposition than the other two orthogonal polarizations. And that's going to effectively increase our cycling rate. But it's a little more complicated than that. So there are several energy splittings here in the ground state, and thus several dark-bright evolution frequencies, meaning that you cannot sort of efficiently wait to empty out all the dark states by waiting for state evolution. For some M sub f submanifolds, there are no long-lived dark states provided sufficient polarization switching. For other M sub f submanifolds, they can possess long-lived dark states because one polarization, dark-bright basis, is addressed only partially by the other polarization. The situation is complicated, and that's where these simulations really come in. So here are some results of those simulations. So we have the excited state population and the ground state population for the 2 polarization case and the 3 polarization case. We'll note that the integrated area, the area under these curves, is going to be, for the excited state, is going to be proportional to the number of photons you cycle. So we can see that by adding that third polarization, we dramatically increase the number of photons we're cycling. And we can look at the ground state population to understand why that is. With only 2 polarizations, we have these hyperfine dark states that are dramatically limiting our cycling. But by adding that third polarization, we start to see consistent cycling throughout that multipass. But we can actually do even better. We can sort of get the best of both worlds, which is we can simultaneously excite both the f prime equals 0 and the f prime equals 1 with our 2 multipasses, with our 3 modulating polarizations. This is sort of the best that one can do. And this should even further destabilize these hyperfine dark states. So here's the simulations for that. Again, ground state relative population, normalized excited state population as a function of time. We can see that all the ground states participate in cycling, and we can see that it appears, sort of visually, that this total excited state visually cycles near completion. And what we can do then is perform the experiment. So here in blue, I have our favorite R1 calibration transitions. They're also shown in the insets. And here I'm comparing the simultaneous excitation with the three polarizations. And in this frame, I'm comparing that F prime equals 1 excitation with the three polarizations. And we're going to do the same thing that we did with those R1 transitions. So again, just to orient ourselves, each row is a calibration transition, a standard candle. Each column is one of these transitions of interest. And what I want to do is focus in on this column. So this is a simultaneous excitation. We can see that no matter which standard candle we use, we're cycling sort of 70 photons. And that's in pretty good agreement with the simulations. And we think this partial disagreement is due to mischaracterization of our experimental parameters. It's something that we're still looking into. But the takeaway here is that we have achieved cycling near the 100 photon limit expected from vibrational branching. We've accomplished this by introducing this third modulating polarization. And what we find is that our simulations are both internally consistent and in qualitative agreement with our experiment. We have certainly achieved sufficient cycling to achieve unit detection efficiency for the Centrex experiment. And our difficulties are related to this large hyperfine structure in the excited state and these small hyperfine splittings in that unresolved ground state. And that's giving us these slowly evolving hyperfine dark states. Moving forward, we are interested in working towards comparing our simulated and experimental cycle times, not just photon numbers. So these simulations can give spatial information just like our camera images. So here we have our fluorescent signal as a function of time for a few different laser powers. So moving forward, that's something that we're interested in doing. We are also interested in adding an additional vibrational repump laser at 278. This should allow significantly more cycling and could potentially allow for transverse cooling. Unfortunately, to further improve the cycling, we need an additional laser or increased laser power. So again, this scheme where we excite two simultaneous transitions with two multipasses with these three orthogonal polarizations, we find ourselves in a place where we're starting to exceed our power budget. And with that, I'd like to finish on our acknowledgement slide. So Amherst College is an undergraduate institution. So these four individuals completed undergraduate theses in our laboratory. I also want to acknowledge Larry Hunter, our PI, and of course Dave DeMille and our friends at Centrex. And with that, I thank you for your attention and would be happy to answer any questions you might have.
Hey. I recall previous setups with the multipass and then with microwave polarizations being modulated.
Yeah.
Is your multipass better at cycling photons than the previous setup?
Yeah. So what one can also do to improve cycling is use microwave transitions. So you could imagine coupling the J equals 0 state and the J equals 1 state with 13 gigahertz microphase. And that can maybe do two things. You could have those be on resonance, and in that case, you would drive population, and all of the molecules would sample all the states. So we've done that, and you do get enhancement from that population transfer in your overall signal, but it doesn't actually speed things up. It turns out that that sampling of all those ground states is slow. The other thing that you could imagine is using slightly off-resonance microwaves. And what this could do is lift the degeneracy. It could perturb the energies of those ground states and maybe make those cycling rates faster. So we also did that. We tried to use off-resonance microwaves, and that also did not increase the cycling rate. The scheme which I talked about is the one that gives us the most photons.
Maybe following up on that, that's a great talk, by the way. also imagine you could explicitly couple these states, either with RF or Raman transitions, to try to destabilize them.
Yeah,
Would
it's
that work?
maybe. I think it's complicated, but we are always interested in coming up with other ways to do it, and there might be a way to do that, possibly.
Maybe you can also follow up this question. So, can you would define like phase module, very fast phase modulation of the convolution?
Um, so
Fast phase depends on the phase. If it's very fast, if the dark phase cannot follow erratically, it's not very fast. Can make convolution.
yeah, so one thing we have tried is to add a phase EOM to add sidebands to the transition in hopes of making it cycling faster, and that sort of helped, but not particularly much.
Also follow up on that. What about cycling for the other hyperfine manifold in the B state, either with another laser or with
Yeah, that's right. So one could definitely get this to cycle if you used 4 lasers to excite all of these hyperfine manifolds. But the problem is that these are rotationally closed, but because these are F1 prime equals 3/2, these are not rotationally closed. So these states, if you excited to them, you wouldn't have hyperfine dark states, but you would decay to the J equals 3 minus. You could have then add even more lasers, so we're at 4. We could then add 4 more lasers to couple them back into cycle, and I think that would work. But you would need, 8 UV lasers, which would be a challenge for us.